Okay, welcome to another Orbiter 2010 video. And this video is going to be a continuation in my Jupiter moon hopping series. We're starting off on Callisto, then we're going to drop down to Ganymede. From there we're going to drop down to Europa, and from there we're going to drop down to Io. Just kind of do a hop from one moon to the other, and primarily for the sake of really learning how to use IMFD. In the last several months I spent a bunch of time with Dimitri recording those IMFD training videos, and he's also spent a lot of time with me off camera helping me learn how to use IMFD. And I feel like I have a pretty good solid understanding of it now, a pretty good intuition for it. So I thought that in addition to those IMFD training videos, it would be good for me to just sit here solo and explain things in the way that I explain them, which is typically over explaining, but that's just kind of how I like to do things because it ensures that people walk away with all the information that they need, hopefully. And yeah, so in the last video, we set up our IMFD plan. We can actually shut that off so that you don't think this has anything to do with transx. We set up our IMFD plan for going from Ganymede down to, from going from Callisto to Ganymede, but there's still some more steps involved. We ran out of time on that video, so we had to stop. And now we're picking up immediately where that one left off. So if you haven't seen that video, definitely go back and watch it, then come back here. Switch camera views, and then we're going to jump back into the planning process. Let's power this side back up. And we're going to bring interplanetary up on this side. Now, we need to do the next step. We've already determined that this is pretty much the very best solution. It's possible that there is still a better solution yet, but as we saw in the last video, we warped time forward by 30, 60 days, and we really couldn't come up with anything better than this. My suspicion is that if we could get the moons to line up so that we could leave at one node and arrive at the other, we may be able to beat this by a little bit, but it probably wouldn't be significant. All right, now, so let's kind of go back to the checklist that we're building here. So after we did that, have a break in our planning so that we know that this was all done in video 1 and this is part of video 2. So the next step is to bring IMFD up on the other side and share it with the other instance of IMFD. I don't want to say share it with side 1 because you don't necessarily know which side you had it on to begin with. So bring up IMFD on on the other side that you don't have it loaded on, and share it with the other instance. So we'll do that now. So we have IMFD up over here, menu, share, and in this case, this is 1, this is 0, so we want to share it with 1. And we want to go to the surface launch program, so PRJ, and load the surface launch program. And set the surface launch program so that it's using the course, which it apparently is by default. But if for some reason it's set on base approach or slingshot or something else, make sure that it's on the course program. Let me put that in the notes. Load the surface launch program and make sure that it's using the course program op mode is what it's calling it here. Okay, now here we want to, it's always best generally to leave when you're facing, when you have a launch heading of 90 degrees. But let's take a look at why that sometimes doesn't matter. Let's bring up Orbit MFD. And we have Callisto as our reference, obviously, because we're on that body. And we can see that the velocity, the rotational velocity from this launch site is 10 meters per second. That's almost nothing. So this means that if for some reason we need to take off and go a different direction, then it's only going to cost us, I guess, at most, an additional 10.11 meters per second. If we get a heading that's close to 90, but not exactly 90, if we get like 80, 100, 70, 120, if we get something that's close to 90, then the additional cost is only going to be a couple of meters per second. So the worst case scenario is that if we had to go backwards, if we had to go to 270 from this launch site, that it would cost us all the velocity of the launch plus an additional 10.11 meters per second. So on bodies like Callisto and even Earth's moon, the moon has almost no rotational velocity, then your heading just simply doesn't matter. On Earth, your velocity from KSC is like 400 and something. It's over 400. So that's quite a bit of delta V. You could imagine if you had to launch backwards from KFC, if you had to, instead of going to 90, if you had to go to 270, it would cost you all the velocity of the launch, which is, 7,000. Well, it's actually like 9.5 kilometers per second when you include gravity loss in the atmosphere. But it would cost you all that plus an additional 450 or thereabout. So that's just something to take into note. You don't have to panic if you can't get a heading of 90 degrees in this case, because we only have a 10 degree velocity. So let's bring back up IMFD. And so on this side, we probably want to set our altitude. It could have some small impact on the heading that we have. Like right now, we can see that if we were to launch right now, our heading would be 169. And again, that's almost backwards. That's almost 180. So the next step, I would say, is to put in an altitude that makes sense. Now, on the moon, I typically go for 20 kilometers. I'm finding in these outer planets that I kind of like 30 better, just because there's so many gravitational perturbations out here that if you have a low altitude around some of these moons, you'll find that after you go around one or two orbits, your periapsis will actually be below the surface. So it's not a bad idea to have a higher initial altitude, even though you otherwise wouldn't need it because there's no atmosphere and there's no terrain to worry about. But just strictly because the perturbations can affect your orbital altitudes around the body, I think it's probably not a bad idea to start off a little bit higher than 20. Maybe even 40 or 50 wouldn't be that horrible of an idea. But we'll set it to 30K. So let's put that in as our next step. Let's see, set the orbital altitude target. I guess I should say set the target orbital altitude. Located right under course program on the right side of the MFD. And we don't know from one body to the next what we want that target to be, so we're not going to put it here as 30 or 50 or whatever, because on the moon, if you were doing this on the moon, you'd only want 20, and on some other bodies you might want something really high for some reason. But we're setting that, and you can see that it doesn't really look like it impacted our heading all that much. Now, Surface MFD also tells us, actually let me think about this for a second, do I need to target Callisto from here, or because it's tied to the course program, does that not matter? Let me see real quick. Or rather, target Ganymede. Invalid target. Okay, so because it's already connected to the course program, I don't need to do that. All right, so target, just hit enter to reset that. Okay, now the only thing we can adjust here are these variables, and we don't want to change this because it's already set. The only thing we want to change here is the altitude. But this Surface MFD also tells us that if we wait 265,000 seconds, we can have a 90-degree heading. Unfortunately, 265,000 seconds puts us well past the time to go. So the best thing that we can do, likely, is just warp time forward until we're at about the time to go, and we'll have a better heading than we have now. I mean, it can't hardly possibly be any worse. But we're not going to be able to get the 90-degree heading, because in order to get the 90-degree heading, we have to wait that amount of time. And if we wait that amount of time, we're going to be like 3 days past the eject point, and that's quite a bit. It would undoubtedly drive our total requirement on our delta V up significantly higher. And again, the only thing that we're going to lose by not launching at the right time is a maximum of 10.11 meters per second. So it's certainly not worth trying to worry about that. So let's go forward in time, and we're watching our heading and our TEJ. This is probably going to come around to 180. Then it's going to keep increasing until we're at, I don't know what it'll be, 0 maybe by the time we get to the time to launch. Now, we do not want to take the time to launch all the way to 0 because we need to take into account the time that's going to take us to get up into orbit. And on Callisto, are we on Callisto? I keep forgetting which planet we're on, or which moon we're on. We're on Ganymede. Let's bring up orbit MFD. Ganymede only has a radius of 2,400. So what is that? Is that equivalent to the moon? Let me just check real quick out of curiosity. I can't see that information because I'm not on the moon apparently. I don't know how that compares to the moon, but I think it's kind of close, so we should probably have maybe similar orbital parameters that we do on the moon. I'd have to bring up a spreadsheet and do a couple quick calculations to know for sure, but we're not going to bother with that. So let's bring interplanetary back up, and now we're going to warp time forward again till we're at time to go. So in terms of our checklist here that we're making, the right time to go is dictated by whether or not is dictated by two factors. The first factor is how close you can get to a 90-degree heading. In some cases such as being on the moon or being on a moon like Ganymede, the launch heading simply does not matter. In situations like being on Earth, which has a relatively high rotational velocity, it's very important to have a 90-degree launch heading. The second factor is your TEJ. You need to launch as close to the TEJ as possible. If launch heading is not a concern, then simply launch at the heading given by surface, what is it called? By the surface launch program. So if launch heading is not a concern, then simply launch at the heading given by the surface launch program when your TEJ is about 1 hour out. That's usually a good number. So in this case, we're not worrying about the launch heading. So we're going to launch when TEJ is about 1 hour, and that's going to be 3,600 seconds. And the reason we say 1 hour is because when we launch, we don't know exactly where in our orbit we're actually going to do the eject. It could be right away, in which case we would actually prefer the TEJ to just be maybe 1,000 seconds. But it could be as far as the other side of the moon, in which case the TEJ might be much higher than that. In fact, I think Dimitri even said to go when the TEJ is 5,000. I seem to recall hearing that. But in this case, we'll go at 3,600 and see what happens. And you can see our heading is improving. It's improving a lot, actually. It may even go past 90 and go farther out the other way, which would be fine. But in this case, as it continues to improve, then the cost of getting into orbit is going down. But again, it's almost insignificant here on Ganymede. Let's go forward a little more. Or Callisto. Which darn planet moon are we on? I keep forgetting. We're on Callisto. Okay. So heading is getting down there. Let's go forward a little more. Yeah, you can see we're going to have a heading that's really close to 90. So this works out really well. And again, now the TEJ is about 5,000. I kind of almost seem to think I remember Dimitri telling me to start setting stuff up at 5,000. But again, let's go to 3,600. And the reason for that is because we don't know when in our orbit we're going to do the eject. If we could time that perfectly, that would be ideal, but I'm not even sure. I don't know if you can do that with IMFD or not. So let's go to 3600, and again, it is improving our heading a little bit. Okay, so we're 1 hour away. I overshot that a little bit. 1 hour away from the time to eject. Now let us, we're gonna now hover up off the landing pad and get into orbit per the usual method. So let's make a note of that here. And we don't really have to bring up orbit MFD because we have, then let me go back to 0.1 for a second. We have the APA here, we have the PEA here. So as we're getting into orbit, we'll have that information. But one thing you do want to do, you want to change the projection probably to self, because when you get up, as you start getting up into orbit, if you have it set on the default, it's going to have those orbital lines are going to be tilted, and it's easier to understand the orbital lines, in my opinion, if you have it set to the projection method. So then, in terms of our steps here, the next step, when you are ready to launch, whenever that is, launch per the usual method and use the surface launch program as your guide to determine your launch heading and to help you stay on target while getting up into orbit. And what I mean by that, to stay on target, is after you take off, you will have a relative inclination in surface launch MFD. Use that as your guide. That's what I mean by that. Okay, now we are all set. Let me just check here. We have rotation, surface controls are off. All right, let's get into orbit. Launch heading is going to be, and we fortunately with IMFD we don't have to memorize it, because when we lift up off the pad it's still given to us, but let's just make a note. 68.836, so basically it's going to be, that's 69, so 68's right there. It's going to be almost all the way over to 69, so we don't need to rotate very far. Putting in enough hover to get up, and now I need to go back to real time. Okay, now we're hovering, and I don't want to put in way too much hover, so let me immediately take some of that out because I feel like I'm ascending really fast.
Translation, rotation.
Fact. For the moment, let me bring up surface MFD so I know what my speeds are here. Oops. Okay, don't do that. All right, rotate over to 68.8. I'm just watching my vertical speed and my vertical ascent to see if I'm ascending or descending. Okay, that's 69. So 68.8 should be about right there. It's almost all the way over to 69. Full power on the main. Eliminate all the hover. And pitch up just a couple degrees. Again, similar to like when you're on the moon. You don't need to pitch way up. Now we can see that our EIN is actually, I need to make a note of that. It's called EIN, not RIN. That's what we're kind of watching to help us determine if we need to yaw left or right. We would like to arrive in orbit with a 0 EIN, but we don't want to fuss over it to the extent that we have other problems with our launch. You can see it's still coming down. And again, we have our APA and PEA here. I'm a little bit more comfortable looking at orbit MFD for this, so let's projection ship, distance PEA APA. And we can see that our time to the apoapsis is, it's not 1 or 2, so that means we're actually descending a little bit. Let me pitch up just a slight amount. And I'm going to put in a little bit of right yaw here in a moment. Well, maybe, yeah, a little bit of right yaw, because the EIN's probably going to get to 0 and then go in the other direction if I don't. So again, watching the APT here, you can see that it's not 1 or 2 seconds, so that means that I'm still technically descending at the moment. I can also see that up here. Now the APT is above 0, so I can pitch back down. And let me yaw a bit more to the right to bring that EIN down. That's kind of overdoing it. And it looks like this is about the heading that we need. And it looks like we're descending a little bit at the moment, so let's pitch up just a touch. But the closer we get to orbital velocity, the less we have to worry about descending because it catches up really quick. EIN is almost perfect, and we're still descending just a touch. It's fine. Now we're going up. You can see the APT value is above 0. Let's go back to the level. And at this point, we don't have to worry about our pitch. EIN is 0, perfect. And again, the APA target is 30 kilometers. Almost overshot.
Translation.
Translate back just a touch. And there we have it. Okay, let's switch over to orbit orbit HUD rather. And I don't believe there's anything I need to put in the notes because that was the step. Yeah, using. Okay, so then the next step, we're done with surface launch as soon as we reach orbit. So just note that. Then the next step is to bring up orbit eject on the side that you have the surface launch program on. So let's put that in the notes. After achieving orbital velocity and reaching the target APA, bring orbit eject up on the side that had the surface launch program. We are done with surface launch. We do not need it beyond this point. Okay, also note that when you bring up orbit eject, it has to be shared with the course program on the other instance of IMFD, but this should already be the case since the surface launch program was shared with the course program. Okay. All right, so we bring up orbit eject. Once we have orbit eject loaded, we need to do similar to what we did before, but this time we actually have to make a change because here it says that higher orbit is the program that it's targeting, and we want it to target the course program. So let's put that in as a step. When you have orbit eject loaded, press plus minus to switch to the course program. Let me not word it that way because we're not really switching to the course program. What we're doing when you have orbit eject loaded is press plus minus to have it use the course program. It defaults to higher orbit. Seems to anyway. Yeah, higher orbit than the plus. Now, once we have that, again, I like to press the PRJ to change the projection just because I don't really like the way that looks. So we can put that in. Optionally, press PRJ to change the projection to self. Okay, now the orbit eject program is telling us how much delta V we actually need to do the ejection, and it's not the same as, and actually let me go back, I'm at 0.1, and we're going to be doing this ejection really soon, so I need to do this quickly. But the orbit eject program gives us a different equation, basically a different calculation. When you figure out the outward velocity using target intercept, this is how much velocity you would need to go from Ganymede, to go from Callisto to Ganymede, if you were in the orbit of Ganymede, but Ganymede itself was not there. So if you were just at that orbit, then you would need that much to get over to Callisto. But since we're starting off on Callisto, and Callisto has its own gravity and has its own influences, this is how much delta V we need, which interestingly enough is actually lower than what we have here. But that's the reason that we have different numbers, because there's the calculation that you're getting from target intercept is saying that, you know, just if you were in that orbit by itself, or like if you wanted to put rocket engines on Callisto and move Callisto over to Ganymede, then it would cost you that number. But since we're not doing that, we're in orbit around Callisto, then this is actually what it's going to cost us. Something to note here is the EIN. It's a 0.00, but if for some reason it were not 0.00, we could do an adjustment on the TIN to bring the EIN down here. And actually, I noticed that there's the EIN here and here, and something I am often confused on myself is whether or not we want to bring it down on that side or that side. It must be this side, because you'll note that as I'm putting it in over here, it's not adjusting anything, so it must be over here. So let me put that in as a step. 20. Adjust the TIN from the target intercept program in order to bring the EIN down to 0.00 from the orbit eject program. So that's kind of maybe a little confusing, because over here we're adjusting this variable to change something that's over here rather than adjusting something here to change what's on that side. But just note that when you make the adjustment to the target intercept over here, you're actually looking at the EIN on that side and not on that side. Okay, we're really close to 30 minutes again already, so let me go ahead and end this part of the video here, and when we come back, we will complete everything that needs to be completed for the actual ejection burn, and then we'll be on our way to Ganymede. If you like this part of the video, like it. If you didn't like it, thumbs down. And subscribe to the channel if you're not already subscribed, so that you can be notified when I upload new orbiter videos. Check the link for description, check the description rather for links to other different things, and I will see you in the next part. Next step. We've already determined that this is pretty much the very best solution. It's possible that there is still a better solution yet, but as we saw in the last video, we warped time forward by 30, 60 days, and we really couldn't come up with anything better than this. My suspicion is that if we could get the moons to line up so that we could leave at one node and arrive at the other, we may be able to beat this by a little bit, but it probably wouldn't be significant. All right, now, so let's kind of go back to we set up our IMFD plan for going from Ganymede down to, from going from Callisto to Ganymede, but there's still some more steps involved. We ran out of time on that video, so we had to stop, and now we're picking up immediately where that one left off. So if you haven't seen that video, definitely go back and watch it, then come back here. Switch camera views, and then we're going to jump back into the planning process. Let's power this side back up, and we're going to bring interplanetary up on this side. Now we need to do the... Okay, welcome to another Orbiter 2010 video, and this video is going to be a continuation in my Jupiter moon hopping series. We're starting off on Callisto, then we're going to drop down to Ganymede. From there, we're going to drop down to Europa, and from there, we're going to drop down to Io. Just kind of do a hop from one moon to the other, and primarily for the sake of really learning how to use IMFD. In the last several months, I spent a bunch of time with Dimitri recording those IMFD training videos, and he's also spent a lot of time with me off camera, helping me learn how to use IMFD. And I feel like I have a pretty good, solid understanding of it now, a pretty good intuition for it. So I thought that in addition to those IMFD training videos, it would be good for me to just sit here solo and explain things in the way that I explain them, which is typically over-explaining, but that's just kind of how I like to do things, because it ensures that people walk away with all the information that they need, hopefully. And yeah, so in the last video, we set up our IMFD plan. We can actually shut that off so that you don't think this has anything to do with transects. The checklist that we're building here. So after we did that, kind of a break in our planning so that we know that this was all done in video 1 and this is part of video 2. So the next step is to bring IMFD up on the other side and share it with the other instance of IMFD. I don't want to say share it with side 1 because you don't necessarily know which side you had it on to begin with. So bring up IMFD on which other